Episode 86, Extragalactic X-ray Exoplanet. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart. Sitting opposite me at the desk in her office, Dr. Emily Brunsden. Hi, Emily. How you doing?
Hello. I'm very well, thank you.
Good. Listen, today we're going to be talking about something which we have discussed on the podcast previously, probably at least once. Actually, I have a sense probably a number of times.
Many times,
because this is a favorite hot topic on the show. Today we're going to be talking about exoplanets. Right, which are not planets in our solar system. Remember, these are planets in different solar systems. They're planets going around different stars. But there's been a little bit of news lately. You might have seen that in your local media outlet of choice. There's been something about a very special kind of exoplanet. Emily, what are we talking about today? What's going on?
So today we've got some exciting news of the discovery of an extragalactic exoplanet.
So there's a lot to unpack in that.
Yeah,
there's
don't
a lot
say
of
that too
X's.
fast.
Yeah, there's a lot of good points in Scrabble, but otherwise, a lot to unpack. So extragalactic exoplanet. So this is an exoplanet in another galaxy.
Exactly.
Okay, who's discovered what, how, why? Let's put some names on this.
Yeah, so this is very exciting. So this is a team which is led by Di Stefano et al., who comes from the university. They come from Cambridge, but the Cambridge that's in Massachusetts,
right,
not the
other
Cambridge.
Yep.
The Institute of Astrophysics there. What they have done is they've been looking using space telescopes, and particularly with Chandra and XMM Newton, two of our favourite space telescopes. They've been looking at the Whirlpool Galaxy, and in the Whirlpool Galaxy, they have detected and pretty much got to the bottom of the detection of a exoplanet going around a very unusual object in the Whirlpool Galaxy.
Okay, so there's a lot going on here. First of all, can I just ask, is this the first time we might have seen a planet in another galaxy?
Wow. Wow.
As usual, what seems to me like a really simple question is it's never simple, is it?
It's all right. I've got a quarter of my notes are on this topic. It's all good. So, yeah, have we been here before?
Have we been here before?
Yes, we actually have.
We specifically, on this show?
On this show.
God, my memory's shocking. Have we talked about planets in other galaxies
We
before?
actually have. Now, before we get to that, I guess the first potential detection of a exoplanet not in our galaxy was H1B9932.
Catchy name.
Yep. This goes back to 1996.
Wow. That's right back there in the exoplanet.
Which is only 1 year after 1995, which is when we...
True statement, but I'm assuming there's reason you've said that.
Well, 1995 was when we first discovered the first kind of ordinary exoplanet, our standard... kind of, this is another planet going around another star.
This isn't some crazy thing that is ridiculous. This is just a planet going around just a star. That was 95.
Yep.
And then in 96 they went, hold my beer, I've just found a planet in another galaxy. Top that.
Yeah, so this is a planet which is in galaxy YGKOWG1.
Again, nice, catchy.
Which is a galaxy about 4 billion light years away.
Okay. And sorry, how? How did they, that's a really long way. I'm amazed you can see anything at that distance, let alone a planet. So sorry, have we talked about this?
We're getting there.
We're getting there. How, Emily? How did they?
Well, so what they
Can
found...
I just point out, by the way, we're so far away from what today's actual episode is about, but that's all right. That's okay. Just to keep going down this one.
This is
We'll come
cool.
back.
Yeah,
Okay,
we'll
good.
come back.
Yep.
Promise you. So this is coming from the gravitational microlensing of a quasar. So a quasar is a really distant, very, very bright galaxy. Some of the earliest galaxies that we have in the universe that we can see, most distant galaxies that we can see in the universe are what we call quasars.
And really bright.
Really bright, which means if you put mass in front of them, say another galaxy, then we get this gravitational lensing effect where the matter bends the light coming from this very distant galaxy into all sorts of pretty shapes and patterns. And this is all due to Einstein's relativity. Photons get bent by gravity alongside, other pieces of matter as well.
Sure, and this is one that's definitely come up in the podcast before. We've definitely talked about gravitational lensing. Okay.
Yeah, so from this gravitational lensing, they think they may have seen a 3 Earth mass planet in this galaxy that's in between us and the quasar.
That's a fairly extraordinary claim because you've got a very, 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 very bright and very, very distant thing being gravitationally lensed, which I thought usually doesn't that require really, really heavy things to show up in a big, like really massive things for that to show up?
Yeah. So galaxies are
So
quite big.
Again, I ask you patiently, how the hell do you see something which is in the order of Earth-sized planet in that way? That's just, none of that adds up. That's ridiculous.
Well, it's just all backtracking and modelling, right? So you got what you see. You can see, what the quasar should look like. You've got what it does look like. So you kind of fill in the blank of what the mass in between must look like. And in this case, they thought, okay, that could be explained by a 3 Earth mass planet. It's a candidate, right? It's not confirmed, but that was just the first kind of maybe there's a planet in another galaxy.
Okay, look, I'm going to go with it. We're not here to talk about that one. That does just sound a little bit nuts to me. But that was 96.
That was 96.
Yep.
Then in 2009, we discovered PA99N2.
Naming's not getting any better.
No, it's not. But this was a little bit closer to home. So instead of being 4 billion light years away, this is a planet in a galaxy, very familiar galaxy, actually. One of our sort of best friend galaxies, the Andromeda galaxy.
Oh, just next door. Yeah, beautiful one, just over there.
It's only 2.5 million light years away.
Yeah. Right, just you could almost throw a stone and hit it.
Yeah. So this one, they think, again, this was microlensing again, so looking at the gravitational interaction. In this case, it's the Andromeda, and then there's stuff in between us and Andromeda that's doing the lensing. And they think that maybe something about 6 times the mass of Jupiter was contributing to some of that lensing.
All right, that's, plausible, sure.
Yeah, okay, kind of. And what's very interesting is then in 2018, so not super long ago.
Yeah, just a couple of years.
There was a very inaugural episode of Syzygy, which was recorded. It was actually episode 1.
Number 1, right the way back to the very beginning. What did we talk about?
We talked about the discovery of 2,000 unbound planets.
That's right, we did.
In another galaxy.
Yeah. Planets which are just drifting. Just wandering around in space without a home. Very sad.
Yeah. So 2,000 of these things, some masses ranging from the moon to, several times the mass of Jupiter. And these were all in this galaxy, which again was lensing a quasar. And therefore there needed to be some extra mass in there that wasn't explained by the stars and extra so on and so on. And so, it came up with there must be a whole bunch of exoplanets kicking around in this galaxy.
Now, that's not saying there, that bit there, I can see a planet there. As opposed to, like, I'm thinking about when we've spotted exoplanets doing transits, for example, in our own galaxy. And you look at a star and it gets a little bit dimmer and then goes bright again and then gets a little bit dimmer. And the interpretation is that it goes dimmer because there's a planet getting in the way. That's a transit, right? The planet goes across the front and you can measure that and you can determine all sorts of things about the planet. And that, to me, is like, that's a planet that did that thing. Whereas the very first episode of Syzygy was more like, we're missing a bunch of mass. Well, what would explain that? And what if we put into our model that there are a whole bunch of planets that don't have home stars to go around, but they're there just wandering free, and what would that do to our models? Hey, it fixes them. Fantastic. So we know that there's planets there, or we think that there's planets there. But that, to me, feels a little bit different to, yep, no, there it is there. Like, I can see it. Right?
Yeah.
Put a pin on that one. I can see it. So that, to me, feels not any more or less as a scientific discovery, but a different kind of thing.
Exactly. And particularly with the first 2 candidates that we had, these were transient events. So that means that you get this alignment where you're getting the piece of matter that's in between us and the background bit of light. Then you just get it once, right? These 2, everything in the universe is moving. So it's moving past or moving through the line of sight that we have to these distant galaxies. So you only ever get one shot at these microlensing events.
You couldn't go back and look at the same thing again now and go, well, there's that planet again, right? We found it again. No, that opportunity is well and truly past.
exactly. So these are always going to be candidates.
Sure.
Because we just don't have a way to follow them up because that lensing is just unlikely to ever occur ever again.
Sure. As opposed to a lot of transit discoveries, or most transit discoveries, where it just happens again and again and again and again and again because the planet's going around the star. And so you just wait for it to come around again, and there it is again. You just saw it again.
So maybe that's why a lot of the news articles that I'm seeing that are talking about this are talking about the detection and confirmation.
So this is today's news. All right. So this is a planet in another galaxy, or a discovery of an exoplanet in another galaxy, an extragalactic exoplanet, but it's confirmed. Maybe? Question mark?
Interestingly, the paper, a journal article doesn't suggest this, but the news do.
Right. Okay. So the scientists themselves are going, hey, look, we're just telling you what we saw. And everyone else is going, fantastic, done, congratulations. Get a photo, arms around each other, that kind of thing.
Yeah.
Yeah.
But what we can be excited about is that this is not a planet that's been discovered through microlensing. This is a planet that's been discovered by a transit.
Wow, a transit.
A transit.
Which is what we do in this galaxy in order to find exoplanets, or at least it's one of the ways. But I wouldn't have thought that's possible in another galaxy, because that's a really long way away and the stars are really small and all close together. And like, how the hell do you do that?
You're quite right in all those points. Yeah, the stars are very individually very faint.
Yeah, like I've seen the pictures.
Yeah, exactly. Even the Whirlpool Galaxy, which is not super far away, right? We've got beautiful pictures of the Whirlpool Galaxy. In some ways, it's kind of the galaxy that's used most often to describe maybe what our galaxy would look like.
Right. Is this the one where we're looking at it really very much top down onto this big spiral galaxy, and it's kind of your archetypal spirally galaxy? It looks like a big whirlpool, right?
Yeah.
Beautiful.
It's stunning.
Okay.
So, yeah, we can't easily pick out the individual stars in this galaxy. And even if we could, they're just not bright enough for us to get enough information from a single star to then pick up what is usually less than a 1% drop that comes from a transit.
Wow. Okay. So, hang on. How far away is the Whirlpool Galaxy?
So we're talking about 23 million light years.
23 million light years. How far away is Andromeda?
2 and a bit.
Right. Now, I know I come back to this every once in a while, but that amazing image of Andromeda where you can see the stars in Andromeda, but it's sort of this wash of what almost looks like photographic noise, like just millions upon millions of tiny little dots really, really close together. But you can see individual stars. Can we see that level of detail in the images of the whirlpool? Like, can you see kind of dots?
Not quite, really. I mean, in isolated examples, yes. And you can pick out things like Cepheids and so on. But not really for your standard run-of-the-mill kind of sun-like star. And even if you could, you're not getting it, as I say, enough to say when a 1% drop is, because your errors effectively are maybe 10%.
Massive, yeah. Okay, so this is all kind of setting the baseline here of whatever the hell it is that they've done. It's really hard. So what the hell have they done? What kind of planet around what kind of star in a galaxy still fairly close but still really long way away could you possibly have a chance of seeing?
Well, you've got to find something that's extraordinarily bright, and you've got to find something that doesn't occur super often so that it's not crowded up in the galaxy. So they're not all kind of mashed together.
As in it's in a part of the galaxy where things are a bit more spread out? Is that what you mean?
Well, you might say instead of having sort of a few billion stars in a galaxy, which get very difficult to distinguish which individual ones, you might want something that you might only have a couple of hundred examples of in your galaxy.
Yeah, that makes sense. That way you can sort of, if you're looking at a patch of the galaxy, you can be fairly sure that this particular kind of star that you're looking at is the one that you meant to be looking at and not a different one just next door.
Yeah. So what we look at is a type of system called an X-ray binary.
Sounds good. What's that? Tell me what an X-ray binary is.
It's one of these nice things that does what it says on the tin, right? It's a binary system, so that means you've got two objects, and that's putting out a lot of X-rays.
Okay. Why would it be doing that? So we've got a binary system, so it's two stars going around each other?
Well, kind of, maybe, because X-rays come from very highly energetic phenomena. So what X-ray binaries are either a black hole or a neutron star. So something that was a star a long time ago has gone through a supernova and now is a very compact object. So either a neutron star or a black hole that's got a companion star that's usually a very hot, bright star. And it's a binary, so they're going around each other, but the other star is close enough that there's material coming off of the big star, and it's falling into the black hole or falling onto the neutron star, and that's generating a lot of energy, including X-rays.
Right. I mean, whenever you get a star like that kind of being, I guess, effectively torn apart, like that's a very energetic thing. So lots of X-rays coming off. Fantastic. So I can imagine how that would be something that you could see, but it doesn't sound like a particularly nice place to have a planet.
Well,
really?
No.
So where's the planet come into this?
Well, okay, so we've now solved our problem. We've found something that's really bright.
Sure.
Each of these objects are probably something like 1 million times brighter than the sun.
It sounds good. You've sold me on the kind of system that we should be working with here.
Yep.
Now sell me on and some of these could have planets, because it doesn't sound like a very planety place.
Well, there's no reason why they couldn't. I mean,
Sure.
We have binary star systems that we know of in our galaxy that have planets. So it's not, I mean, we can talk about planets that were either part of the original star system. So they'd have to be sort of a little bit further away so that they don't get kind of torn apart by the gravitational interactions of the binary itself. So it's kind of like you got your two stars in the middle and then there's a planet going around the outside of those two.
Yeah. As opposed to a planet going around one of the stars, which is then as a system going around the other one, or is it the center of mass? Like that, particularly in this case, I would have thought that'd be just really awful.
Well, it's not. It's just not going to work.
No, that planet's not going to last very long at all.
No, it's going to go straight to the black hole / neutron star.
Bye. Yeah.
So, maybe it was part of the original system that those two stars were born from, or maybe it was captured at some point later on, and it's in kind of some orbit around the system.
Okay. So what have they actually found then? Tell me about the system that's been spied.
Cool. Yeah, so it's got another catchy name, M51 ULS1.
Well, it's slightly shorter than some of the other ones you've read out today anyway. It's slightly catchier, but yeah, go on.
So what we've got here is a X-ray binary. We don't know if it's a black hole or a neutron star. It's not easy to sort of break that down.
Is there a way to tell in general?
I'm not sure. It's in this case, the information we're getting is just the X-rays, which would come from either.
Right.
So it's really hard to say. But what we do know is that there's a companion that was observed, and we know that the companion is a B-type star, which are these really big, hot, bright stars, quite young stars. So we know that this is not a very old system because star A has gone through its entire life cycle and become black hole / neutron star, and star B is still there, and even star B is only maybe at the most 16 million years old.
Right, which is young for a star.
It's really young.
Is there any possibility that they might have formed separately and then become entangled, or is it likely that they would have been together from the start and then one of them's already gone boom?
It's most likely they were born together as a binary pair. Yeah, it's very unlikely to capture in that short space of time, because remember this B star's only been around.
Yeah, well that's
for
true.
A while, right?
That's true.
So, and what we got here is that neutron star is eating some material from that star, generating some lovely X-rays. And you can look at those, and they're really, really nice X-rays to look at. There's all sorts of interesting information you can find out. But what the study saw was that during their observations of the system, then they actually saw a dip. They saw for about 3 hours, the light went out, if you like, on this star. And this was very suspiciously looking exactly like the light curve for a transit.
We've seen this before, said the astronomers.
Yeah, exactly. So they had actually weren't sort of sitting there staring at this particular object. What they were doing was using both Chandra and XMM Newton to X-ray space telescopes. And these space telescopes have been observing this galaxy and a number of other nearby galaxies for quite some time in kind of survey mode. So what these scientists have done, which is very clever, is gone back and said, well, in theory, we've got this many systems. Maybe some of them should have planets. So let's just have a dig around and
Sure.
like write a computer program and see if we can catch any of these things.
Can't hurt to ask, can it? Yeah. And computers are really good at looking back through loads of data, which would just send a human being mad and just go, no, that's fine. I'll sit here and just keep churning through. And looking for that kind of characteristic dip.
Exactly. And this one popped.
Wow.
Which was quite cool.
Cool. Was it just the one dip or is it a repeating
Just
dip?
one.
Just one. Okay. So that kind of gives you we've seen this before, but gee, it'd be really nice to see that again.
Yes. Well, so I guess your first thought is this real? Is this a really, these are very exciting systems, very highly energetic systems. They do all sorts of crazy things, these X-ray binaries, right? So you sort of go through, and this is what the paper has done, is gone through a list of kind of, these are all the other things that we thought this dip could be. Let's try them out and see if they are those things. And if they are, then all we're left with is planet.
Yeah.
Kind of thing.
Yeah. I mean, get rid of all the other possibilities, or at least try them out. That's kind of what you got to do as a researcher. You can't just sort of wade in with your favorite hypothesis. You got to test it out. So they managed to.
Yeah, I mean, there were three sort of main things that you could imagine would be other explanations for what we've seen.
Okay.
So the first one is, could it be a cloud of gas or dust that's just kind of passed in the way? I mean, these are obviously materials being ripped off a star. These are dusty systems as well. And even if we think about more recently Betelgeuse, we think that those clouds of gas and dust sort of partially obscured Betelgeuse.
Yeah. That you're talking about Betelgeuse. It's an enormous star, which we think is going to go supernova at some point, but there was all sorts of stuff all over the press. Last year?
Oh, 2 years ago.
Within the last
think,
couple of years, where astronomers were going, hey, Betelgeuse is behaving a bit weird. It would suddenly go quite dim and then get brighter over a really short time frame. And people were going, it's going to explode. No, wait. It's probably not about to explode. But what is going on? I remember a lot of headlines which were, don't know, this is really weird. And that seems to have settled out to, it was probably dust.
Probably clouds of, yeah. I mean, and related to Betelgeuse itself and its atmosphere. But, that's the kind of dimming that we're talking about. And the reason why this particular phenomenon is ruled out is because if you imagine you've got a cloud of gas and dust that's passing in front of a star that you're looking at, then you wouldn't expect that to be any kind of uniform thickness or uniform size or uniform shape.
No, you wouldn't expect a perfectly spherical cloud of dust or whatever to just wander across it. Like this would be all over the place. It would be quite random. Yeah,
so you'd get some sort of dark dimming, then some bit of brightening as it got to a bit that was more thin, and then it got thicker again. And even the colour of the star that you're watching would change because it reddens when you look at it through dust and so on. So because of all these things, then if you compare that to the transit that was seen, which is a very sharp drop, it's really like, you're coming along at a certain level of brightness and then you just plummet. It's a cliff edge that you fall off here. So there's just not really a plausible way that a dust cloud could do that.
It doesn't look like a dust cloud. It's still looking like a planet getting in the way. Yeah. It's got that kind of thing. Okay. So, all right, let's assume it's not number one.
No.
What's number two?
So you could say, well, maybe it's the natural flicker, if you like, the unstableness of this system. These kind of systems generate all sorts of flares, nova, that kind of thing. They're not stable there's exactly the same amount of mass that's pouring onto the black hole.
By their nature, these are violent things.
Yeah.
So you'd expect their characteristic behavior to be fairly violent. And so maybe this was just having a bit of a slow day.
Yeah.
Maybe,
yeah. So it just could have quietened down for a little bit. Maybe there was less mass.
So we can test that hypothesis?
Well, yeah, because if you look at the observations that we have, the light kind of just went dim for about 3 hours, right? Now, if you'd expect that to be just because of the natural variation, then you'd think that the temperature of the X-ray binary and the color of the X-ray binary would change because it's gotten quieter. So it would sort of cool down, become a little bit, more stable in a way.
I mean, if you're talking about a fundamental change in the behavior of the thing over that period of time, then surely all of the behavior of that thing, like the color of it and all of that, would change too. Like it's the thing itself that is changing, as opposed to a transit, which is where it's just something getting in the way. The thing itself has remained doing what it was doing. That shouldn't change. So
no temperature change, no color change, as far as we can see. And if you want to make that happen with this kind of systems, turns out you've got to actually shrink the X-ray binary part of it by about 3 times for 3 hours and then pop it back up again.
Which sounds like you're going a long way to explain something.
It doesn't seem plausible at all.
Yeah.
Just become a third your size for 3 hours? I don't know.
There's another more plausible explanation going on here.
Yeah,
Occam's
exactly.
razor kicks in at that point, I think. Yeah.
So then you can say, well, okay, it's something's definitely blocking it.
Right.
What's blocking it?
Okay. So we're on to number 3 now.
Yep.
3 of 3 possible other alternate explanations.
Yeah.
So what else could be blocking it? We've had gas.
Yeah.
We've had change in the thing itself. And now something else blocking it. What?
Well, there could be other things, right? We've got other things in galaxies. We've got small stars, we call M dwarfs. We've got failed stars, which are called brown dwarfs. So things that are kind of in between the smallest star and the biggest planet. So they're just kind of lumps that didn't quite make it.
Yep. Could have just wandered into the path.
Yeah. So could it be a small star or a brown dwarf? One of the problems with that is that the system's very young.
Mm-hmm.
So you can't have anything that's taken any sort of time to evolve. And even for the smallest stars that we have in the universe, the smaller you are, the longer it takes for you to form, because you just don't have the gravitational pull to pull yourself together quickly.
Okay, all right.
So big stars form very quickly, lots of gravity. Small stars take ages.
Take a lot longer. All right.
In fact, much more than, say, a few million years to form. So it's probably, a small star would be fairly implausible.
Right.
But even more so, then they've modeled kind of what the radius of this object should be. And this is, I got to say, my favorite plot in the entire paper, because it's just one of those plots you just look at and you're just like,
This is the lovely thing
that's
about
nice.
when you talk to researchers, and they get joy out of things that the rest of the world would look at and go, huh? And you look at it and go, that's great. Look at that plot.
Well,
it's so good.
It's just a really good plot.
Look at
I have
that
to say.
graph. Look at the way the line does the thing. Yeah.
It's really nice. Well, it's also really nice when researchers present their information in a way that even if you're not from that field, you can instantly see what they're talking about and what they're getting at.
I've got to say, visualization of data, it's a big thing. And when it's done well, it's a thing of great joy. So, okay, what's on this fabulous plot?
So what they're looking at is, from the models of the transit, what's the possible radius? And it's a range, right? You could get a radius from X to Y, and they've plotted that as a probability. So there's kind of a peak probability of how the most likely radius is, and then it's kind of gets, as you go smaller or bigger from that, it gets lower and lower, the probability.
Sure. So we've got the signal coming from the X-ray binary, right, which dips. And so on the assumption that something's getting in the way, you can then model how big would that thing have to be to give us what we saw? That's exactly the idea, right?
Yep.
Which is presumably why a minute ago you were talking about your failed stars or your small stars and so on. If it's too big, like there's no way this could be a big honking star getting in the way, otherwise we just wouldn't see anything, right? It would just block it out entirely. Well, why can't we see it anymore? It's because that big star's in the way. Like that doesn't work. So it's got to be small.
Yep.
But this is now modeling, okay, but how small?
Yeah. And then so on the same graph, you've also got marks showing you how big, say, Neptune is, Jupiter, Saturn, and then it goes bigger and bigger and bigger.
Right.
This is the distribution of all the...
I'm liking this graph.
Oh, you got to see the graph.
This has got me written all over it.
And you can see what all the range of sizes that we've seen for the hot Jupiters, the big planets that we found around other stars in our galaxy. Then going up to the brown dwarfs, then going up to kind of M dwarfs, the very smallest stars. So all of that's on this diagram showing you where all they are, how big they are, etc. And then you see where is the most likely radius falling, and it falls spectacularly in between Neptune and Jupiter.
Wow. So I mean that's big for a planet, but it's like that's well and truly within not just the realm of planets that we know of. Like that's our solar system.
It's basically Saturn.
Yeah. It's right there, smack bang in the middle. Like if that had come out as, yeah, but we just never see planets like that. like it just doesn't happen, then that would have been, okay. But falling in the well and truly in the range of, no, we've got one of those. Like we literally have that up the road. It's got a big ring on around it. You might have seen it. That's really cool.
It's very cool.
How big are the error bars on that? Is it everything from, well, basically it could have been the moon through to, the biggest thing you can imagine? Or is it, no, it's reasonably well constrained?
It's reasonably well constrained, so much so that when you get out to the point of being kind of a failed star and beyond, so not a planet anymore, then you're talking about less than 0.5% likelihood that's the radius of this exoplanet.
All right. So it's kind of sounding planety.
It's
Emily.
Very planety, isn't it?
Yeah. So where are we? Just summing up then. In another galaxy, we've seen a very special kind of star system, an X-ray binary, which had a dip, singular. And when you look at that really, really carefully and go through all the different possible ways that could have happened, you're left with, but it kind of just looks like that was a planet. So is it possible that was just something wandering in the path? Like, can you get any information at all about how far away that planet might be from the stars?
Yeah, so we think it might be somewhere on the order of tens of astronomical units.
Okay, and putting that in the context of our solar system, like how far out, for example, is Saturn? Just picking that one.
I can only remember Jupiter's 5. Saturn's maybe 8 or something like that.
Right,
it's further out than the big planets in our solar system broadly.
Right. But then again, as we said before, you'd kind of expect that given the uber violent nature of an X-ray binary. You're not going to find much closer in. So my question really was, what's the likelihood of this being a planet orbiting this system as opposed to something that just wandered into the path at this point in time?
It's very hard to say. I mean, It's probably a planet. But what we would normally ask for in terms of the gold standard of going from candidate planet to confirmed planet, particularly for transits, what we're looking for is to have 3 transits which are equally spaced.
Right. And we have how many?
One.
Well, I mean, I guess you've got the equally spaced part, one transit equally spaced from itself.
Right.
No, okay. We can't even get that.
No.
So we got one. And the problem is we don't even know how long you'd have to wait. Although I guess you could guess, given that it's in the tens of astronomical units, that kind of then tells you how long it would take to orbit.
It would roughly take maybe 70 years to come around again.
And when was this done? When did we see this?
Well, the first detection was 2020, so it's last year. So
right. So
the data might be a little bit older, but
we've got a bit of a wait.
Yeah.
Damn it.
It's a bit awkward.
Like that's not even. Like it wandered through my mind earlier. Like, do we have any historical things that we could look at? You said this was sort of part of a survey. Maybe there's some data. No, there's not a chance that we have anywhere sitting on a hard drive another view of this. This is just, it is what it is. We have this one dip.
Yep.
So where does that leave this bit of science then?
Well, I guess where it leaves us is that we still have 4 and 3 plus 2000 now.
Yes. Putting the 2000 into a different category. Yeah.
Candidate extragalactic exoplanets. We've just found one using a completely different technique.
So the cool thing about this story is it seems reasonably conclusive. I mean, this is a big question mark, I guess. It seems reasonably conclusive that this was a transit.
We can't think of anything else it could have been.
Right. I mean, once you get rid of all the other possibilities as best you can, you're left with seems planety, seems transity, which is really cool because that's, as we mentioned, just to bring this back up again, this is in another galaxy and we've never done that before. And that's very, very cool. So I guess in a sense, it's a sort of proof of principle or I don't know, is it strong enough to be a proof of principle? It's a tantalizing possibility, isn't it? That this is something that we could do more of in a kind of targeted way.
Yeah, absolutely. So it's not shattering our records just yet, but I think it's taking us to that next step, which is very exciting.
Exoplanets in our galaxy, right, have become the biggest thing since sliced bread. Like, it's all over the news, and there's a lot of research going on, and it's very, very exciting. And we can do a lot of it because a lot of the stars are just there, right? It's in our galaxy, and we can look at them and we can study them really, really closely, right? We've just seen this possible exoplanet in another galaxy using the transit method. Is it more likely that that's just, well, that's a curiosity, but there's no way that you could actually form a research program around this because that would be farcical? Or could this kick off a whole new kind of extragalactic exoplanet hunting research area? Where do we sit on that? Like, where does this research sit within astronomy, I guess is what I'm asking.
It's very interesting. So I would say we're not going to be going out looking for exoplanets in other galaxies for the sake of it. It's hard enough finding them in our own, let's be honest.
Yeah.
So what we're really trying to do here is use exoplanets as other links to other science that we're doing. So, if this does turn out to be a real planet around an X-ray binary, it does tell us that is possible. So is that something we need to think about when we think about models for forming X-ray binaries, that they can form planets at the same time? Or do we only have this capture method that we can use? And, what is the overall contribution of planets to how the makeup of a galaxy sort of comes together?
Looking at a planet going around an X-ray binary, it just seems like a really long way to go to look at it in another galaxy. Like, could we have got that information about X-ray binaries in this galaxy? We must have loads of them in the Milky Way that we could have spotted this with. I guess what I'm really trying to get at here, Emily, was this just an absolute chance fluke?
So we do have a few in our galaxy. I think Cygnus is one of the most famous ones. That's a black hole binary system and not super far away. But I don't know if we've got a lot of examples in our galaxy. And remember, the way we look at our galaxy is just awkward, right? We have to look through the disk of the galaxy. So it's actually not super easy. In fact, I was going to give you another stat attack today.
Go on
just about general kind of exoplanet science, just to give you the kind of the context of where we're at in our own galaxy.
I'm always up for a stat attack. Hit me with it.
Our Milky Way galaxy is kind of roughly 100 to 150,000 light years in diameter.
100 to 150,000 light years. Yep.
What's the furthest exoplanet that we've found that is confirmed?
100 to 150,000 light years. I'm going to guess reasonably close, but I'm going to say half of that. I'm going to say the furthest one is half of that. So radius, which is, let's call it in the order of sort of 50 to 70.
So we've only found ones that are up to 28,000 light years away.
Really?
And that's really like the outliers, if you like.
Wow. So we are actually looking really close to home.
They're not easy things to pick up, right? Right.
Can I just ask, before we move on from that?
Go on.
Is that partly because, as you said before, looking into our own galaxy is actually pretty awkward because there's a lot of galaxy in the way. Like, if you want to look at stars a long way away, you've got to look through a lot of galaxy to look at the stars which are a long way away. And there's a lot of stuff in the galaxy. There's a lot of dust and things like that. So it's actually really hard to do. And we're kind of limited to the nearby ones. Is that the idea?
Yeah, well, exactly. And also, if you think about our planet hunters that we've had, their most successful planet hunter, Kepler pointed in the constellation of Cygnus, which is not in the plane of the galaxy, right?
Right.
So we're not pointing at that through the galaxy per se. We're pointing, I think, well, it depends on which way you call up, but
sure.
Let's call it up above the plane of the galaxy and sort of looking at more sparsely populated area of sky, just because we need to have, chips are only our CCD chips that we take our pictures on. You can't have 3 stars on a single pixel because you're not going to be able to tell which star is which.
No, that's a fair point. And how many planets has Kepler roughly
That
found?
was going to be my question for you.
Oh, okay. Right, I'm getting ahead of myself. Okay, so that's stat attack number 1, and I failed that one. We're looking pretty close to home. Go on.
So how many have we got?
It's in the several thousand by now. I want to say 4,000.
Not bad. Well, on the 19th of October 2021, we are up to 4,538.
That was pretty good. Okay, I'm going to take the point for that one.
Confirmed exoplanets.
But I mean, like talking about what you were just saying a second ago, like how many of those are from Kepler? Like,
well, that was going to be another question of mine.
Okay.
Well, let's start first. How many different ways do we have to discover exoplanets? How many techniques have
we've talked about this, but I can't remember. I'm going to say 3. Don't ask me what they are. Transit, and the other ones. I can't remember.
Well, we talked about 2 in this episode.
Oh, we did. And microlensing.
Yeah.
Yeah, transit, microlensing, and the other ones.
We've got 11 different
11
ways.
different ways.
So far that have been successful.
You astronomers are just so clever.
Yeah, most of those, to be fair, have only picked up a handful.
Right.
But
right. Is transit the most productive?
It is the most productive. Do you
Yeah.
want to have a stab at what percentage of that 4,000 have been discovered by transit?
I'm going to say 90.
It's not quite. It's 76.
Okay. That's still very good, but not as not as big as I thought.
And the percentage discovered by microlensing, just because we talked about it?
15?
About 2 and a bit. Only about
I
118.
don't know why I bother even doing this. Yeah.
It's fun, honestly.
Yeah, but you know all the answers.
I know.
I'm just
I wrote them
throwing
down.
my ignorance out there onto the airwaves.
No, it's all good. Yeah, so about 118 we've discovered with microlensing in our galaxy.
Okay, which is not terribly many. Okay. No. But what I was going to say a second ago was like, so if we've got that many through transits, and I mean, you said Kepler was, the big one in this field to date, and it's looking away from the galaxy plane and sort of up into a relatively free patch of sky in order to do that. And we're looking pretty close to home in terms of how many thousands of light years. It just really hits home how many bloody planets there are. Like there must be loads out there. Isn't it like on average, every star has one?
On average, yeah. Maybe even more than one.
Wow. Okay. So where does that leave us for today then? And I love the way I always take some credit for this as well. We humanity have discovered, we think, maybe an exoplanet going around a star in another galaxy, and it's sitting out there as a discovery which is awaiting confirmation, but we might be waiting a really long time because we need that gold standard of 3 different transit events, 3 different measurements, 3 different dips. And we've seen one, and the most likely possibility is that it's going to be, maybe another 70 plus years before we see the
Unfortunately,
next one? Yeah. So that's a really long research program for someone's PhD thesis. So this was all sort of reported reported in the press with sort of breathless headlines of, hey, we've seen this thing. Would astronomers agree that this is a discovery, or is this more of a sort of an arched eyebrow of, that's kind of cool? Who knows?
Yeah, I think it's in between, if I may be so, bold to say what all astronomers think in the world. But because I think it's, as you say, it's pretty much proof of concept of the technique, which I think is really cool. And I think that's actually what the bottom line is here, that this is really clever. I would have never thought, lots of stars in other galaxies, really hard to find exoplanets. That would have been kind of the end of my thought process on that. But no, other people thought, but we got these other types of objects which are bright and easy to see, and we could measure exoplanets potentially going around them. Like, oh yeah, that's cool. Very interesting, very thoughtful. So I like that they have used that technique and been able to see something which is, in all honesty, very likely a planet. But is it kind of like the first planet discovered in another galaxy? Not to the gold standard yet. Could there be another X-ray binary with a planet discovered in another galaxy? Maybe. But maybe they're all on these really long orbits, so maybe we just don't get a chance to see them. So, yeah, to me the value is more in the technique and finding out more about these crazy X-ray binary systems than it is about holding the world title for first extragalactic exoplanet.
Yeah, it's intriguing, isn't it? It kind of falls into that basket of scientific discoveries, which is, I guess we'll never know. But you're not necessarily in it for we've absolutely nailed that one down as how far can we go with this tantalizing but mysterious bit of data.
Yeah.
How much does it look like what we think it is, even if we never find out?
Scientists really set up themselves in research programs to be the first to discover whatever. I want to discover the first blah, whatever it is. That's rarely what we're trying to do. More often than not, we're trying to develop an understanding of something. And, you know, if we can find out maybe some more about some object that we haven't seen before, then that would give us a piece of that puzzle. But it's not really a kind of Guinness World Records of Astronomy competition. Unless you're writing a grant proposal, then I'll give you some slack on that.
Right, well, that brings us to the end of another episode of the show. And Emily, as ever, my brain is filled with ridiculous statistics and a lingering sense of the fabulous possibilities in astronomical research. I love the way that in this story, at the end of the day, we're kind of left with a feeling of, well, that might have been what we thought it was, but basically, we're probably never going to know, which is kind of cool in a way.
Yeah.
A little bit disappointing, maybe, but on the other hand, that we can do it at all is absolutely staggering.
And a reminder that, you know, X-ray binary research is really cool and interesting too.
Well, there is that. There is that. I mean, if you're going to go and find an exoplanet, do it around an X-ray binary. Then you get win-win, right? X-ray binaries and exoplanets. Anyway, time to finish this one up. Emily, if people wanted to get in touch with us and talk to us about how fascinating X-ray binaries are, or that they have a candidate for an exoplanet in another galaxy that we haven't spotted yet, how could they get in touch with us? Is there a way?
There's more than one. You'll be pleased to know.
Oh, spoiled for choice.
So we got some tweets that can happen. I mean, they come to us when you send them to us, so long as you send them to @SyzygyPod.
That's right. If you don't send it to @SyzygyPod, we'll never know. So that's the best way to do it on Twitter.
Exactly.
Yeah.
Yep. So you can tweet us. You can grab us on Facebook, which is, if you look at, you put in the box thingy that you've got at the top there, SyzygyPod.
It's so much less satisfying on Facebook, isn't it? Like @SyzygyPod on Twitter, that's easy. On Facebook, just go and find us. We're out there somewhere. On Facebook, we're doing that thing. And the Instagrams?
Instagrams.
Yes.
There's pictures, I understand.
There are pictures, occasionally little videos of little excerpts from the show, which we throw up on there, which is kind of fun. @SyzygyPod on the Instagram. Do you know where else we're at? @SyzygyPod, and that's on patreon.com, which is where our financial supporters can financially support us. If you're interested in helping us out here on the show, keeping the electrons flowing through the website? Did I mention a website? Syzygy.fm. Then you can do that through patreon.com/syzygypod. And we have a bunch of people who financially support the show and help us to do the thing that we do. Huge thanks to everyone who has been involved and gets involved in the future. But of course, the other way that you can support the show is just by telling everyone you know who's a bit of a space nut that there's this thing. It's called Syzygy and you should listen to it. Go and find it. It's on the interwebs. It's on your podcast catcher of choice. Go and do that, and that'll help us out, rise up through the noise and reach as many science space nuts out there as we possibly can. But listen, we'll be back again in, I don't know, about a week or so. We seem to be getting on with this new modern weekly schedule that we're doing here, Emily, and I think it's working. I like it. So we'll catch you again in a week. See you later, Emily.
See you later.
Bye, everybody.